So good morning, everyone. Let us continue with yesterday's algorithm, that is the Peterson's algorithm for interprocess synchronization. So I already mentioned, originally what I shared with you was this algorithm. Even before the algorithm, the data structures like shared things are the turn variable, where it indicates it is boosted whether process 0 or 1, and flag for every process, so flag of 0 and flag of 1, which indicates that whether that process is ready to enter the critical section or not. So for example, if I say flag of 0 is equal to true, this implies that process P0 is ready to enter into the critical section. And then this is the algorithm. So actually you can think of this as a pseudocode, more near to C programming language. And this is the algorithm for process Pi, where this process is I and other process is considered as a J. So wherever you find J, it is the other process. Just to make it simple, what I did is I repeated the same code. Now look at here. The same code is there. Now with some labels also. So boolean flag of 2 equal to false. So initially both are false. That means no process wishes to enter into the critical section. And term is the variable. Now, as I already mentioned, this is code for process 0, and this is the code for process 1. So P0 and P1, right? The same thing is written here. Only thing is it is in terms of I and J. That is the only difference. Okay. Now see what happens here is, so flag of 0 equal to true, meaning of that is now this process is ready to enter into the critical section, right? But now it assigns turn to P1. Okay. So these two steps, exactly same thing happens here. Now only thing is here, because this is process 1, other process becomes process 0. Whereas in first case, because this is code for process 0, other process becomes 1. Okay, so to make it simple to understand between I and J, as I already mentioned, if I say value of I is equal to 0, J becomes 1. If the value of I is equal to 1, J becomes 0. It is like other process. So the meaning of this is the process marks its willingness to enter into the critical section by setting its own flag to true. Note that they are initialized to false initially both, and now we want this kind of stuff. So for example, this process want to enter into critical section, it mark flag to true. Same thing is done by. Now you can imagine something like one statement executed, then it will be printed, P1 is scheduled, first is again executed, again it is printed, P0 is scheduled. Just to make sure that even though anywhere preemption happens, anywhere your process is interrupted, that doesn't create any problem. Okay. Now have a look at the while loop. The same thing is also written on this, while flag of J and turn equal to J, and directly this is given there, just colon. So just to avoid that, what I did is I just given opening and closing, so it is empty. You think this as a busy wait, right? So while flag of 1, that means if other process wishes to enter into the critical section and turn is equal to 1, that means if it is turn off other process. You easily read this like if other process wishes to enter into the critical section and if it is turn off that process, what you will do? You will simply wait. Same thing is checked here by other process also. If previous process 0 wishes to enter the critical section and if it is turn off that, you simply wait. Now you imagine flag of 0 is true. Let me select some other color. Okay, fine. So here, for example, suppose this first statement is executed. So flag of 0 is true and preemption happen and this is executed. Flag of 1 is equal to true. Now this statement is executed. Turn is equal to 1. Now this statement is executed again. Turn is equal to 0. Now even though in case of a flag, there is a separate flag for every process, turn is shared between both. So after execution of this, remember both the processes wish to enter into the critical section. But now turn set process 0 set it to 1 and process 1 set it to 0. Right? Now if you check it here, flag of 1 is equal to true. Yes, it is true. And turn is equal to 1. No, this time this condition is false. Why false? Because turn is assigned to 0. Right? That means it won't go into the busy wait. Access to critical section is directly granted to first process. Now suppose this process is in critical section and preemption happen and it comes here. While flag of 0 is true, yes, flag of 0 is true because that we have said. And turn is equal to 0, yes, now turn is equal to 0. That means this process has to wait here. So this makes sure that only one process will be in the critical section. Once this process, so that means it is waiting only. It is in while loop only. Once previous process finishes its critical section, it will set flag of 0 equal to false. That means now this process don't want to go into critical section. Actually, it has already done with that. Right? Then suppose this process is again selected by the scheduler. What will happen? Flag of 0 false. So first condition become false. Flag of 0. So false and anything is false. So it will come out of this while loop and then access to this process is granted. So it will go to the critical section. Right? So this is how Peterson's algorithm works. The assumptions I already mentioned. The changes to the variable like turn flag 0 and flag 1, they propagate immediately and atomically. Atomically is like without interruption, like the operation is indivisible. Okay, either complete will be executed or nothing will be executed. That is what is its meaning is. Right? So this is the Peterson's algorithm. Fine. Now let us go back to our original set of slides. Remember that Peterson's solution is very simply provable that the three requirements are met. CS is like critical section. I mentioned 4 requirements, but here they have given 3. So mutual exclusion is preserved because any process TI that will enter the critical section only if flag of J is equal to false. That means that process don't wish to enter into the critical section or it is turn of this process. Well, this is turn of this process. No other process will go into the critical section. That means at most one process will be there in the critical section, and that is the condition of mutual exclusion. Right? Second thing is, as we So progress requirement is also satisfied, because if this process don't want it to go like in the critical section, the flag of this process will be false. And because flag of this process is false, other processes are free to enter into the critical section. So progress requirement is satisfied. And of course, this bounded waiting requirement is also met. A simple trick is made here for bounded waiting. Even though you wish to enter into the critical section, actually you set the turn to other process, right? So definitely you are giving chance to other process. So there is a bounded waiting time. So we are not like one process do not block other process. So Peterson's solution met all three requirements. Only problem with Peterson's solution is it original design is for just two processes. Number one. Number two, if I want to enter into the critical section, I should information of other processes. Why? Because we are setting turn of other processes, right? So like in process 0, we set turn equal to 1. That means I should know the identity of other process, and that is really very difficult. If you see, if the process ID is considered as a PID in what we see, if that is considered as unique ID for a process, every time you create new process, you are getting new process ID. How you will keep track of those process IDs? So that is one difficult thing. And the most important part is there is an assumption about whatever updations we are making, vector is equal to I. See, very first thing, how we started our discussion with is something like counter plus plus. And even though counter plus plus is single statement, actually it results into 3 machine level instructions. Same thing could happen for turn is equal to I. How you think like this is atomic, right? So there is no guarantee that Peterson's solution is flagged and the turn variables updated atomically. There is no support from operating system at all. And for that purpose, what we have to do is we need to think for some other solutions for mutual exclusion. Now, one of the solution is something like hardware support for mutual exclusion, and this hardware support is required for synchronization. Now let us talk about the hardware support, how to utilize it. Okay, so many systems provide hardware support for implementing the critical section code. Let us start with the simplest solution of, say, single processor. Overall, as I mentioned yesterday, it is based on the idea of locking, right? So whenever you wish to enter into the critical section, you need to acquire the lock, right? Once you acquire the lock, so it is something like each and every critical region will be protected by locks. Whoever want to use that resource, shared resource of course, then process has to acquire the lock. Once you acquire the lock, use it. Once you finish using that, release the lock. That is very simple protocol. Okay. Now one simple trick is played with uniprocessors. That means if you have a single processor, if you studied 885 or 886, there are few instructions, something called as the EI and DI, enable interrupts and disable interrupts. Very simple thing, like they are playing with the idea of how we are switching from one process to other process. Whatever the preemption we are talking about, one process will be interrupted and other process will be selected by the scheduler. Right? Now, why one process is interrupted? Because interrupts are enabled. Now, this solution works around that only. Whenever you want to go into the critical section, fine, you simply disable the interrupts, so preemption won't happen. So disable the interrupt, one process will go into the critical section by disabling interrupts. Now interrupts are disabled, so preemption won't happen. That process cannot be interrupted. Once you finish the critical section, then you can again enable the interrupts. Very, very simple instructions are there for that EI and DI. Okay, enable interrupt and disable interrupt. Okay, but then the problem is, will this solution work with multiple processors? No. Reason behind that is very, very simple. EI and DI, these instructions are limited to that processor only. So if I have two processors, if one process is selected on processor 1, next process is selected on processor 2, what will happen is you cannot disable interrupts of other processors. So this is inefficient solution for multiprocessor systems. Okay, and this also creates some sort of problems with, say, clock, because if you see how clocks are implemented is, there is a kind of a timer interrupt which is occurring at fixed interval, and once that timer interrupt is occurred, time is updated. And if you disable the interrupt, that timer interrupt is also disabled. So this will result in longer the critical section, there will be more time difference. There will be more time difference. So that creates a problem. So this is not acceptable solution with disabling interrupts. Okay. And for that, few modern processors, they support some sort of atomic hardware instructions. That means the instructions can be utilized because that is a single instruction that is atomic. Okay, atomic is what? Non-interruptible or indivisible. Fine. Two such instructions are there. One is test and set, and second one is compare and swap. So the first instruction is like TS, test and set, and second instruction is compare and swap. Note that these two instructions are atomic, number one. Now let us go with, first of all, test and set. So you will come to know the idea. This is the overall idea of using locks. Now how to implement these locks? Like previously, as I mentioned, if I say this as a disable interrupt and then enable interrupt, but problem with this is it won't work with multiple processors. Okay, so acquiring lock and releasing lock, we can utilize hardware instructions supported by the processor. Okay, so that now we want to say for example, test and set. Now let me move to, for example, here, set. What this instruction does is test a lock. Testing a lock means checking the value of it. Okay, so test a lock, what it does is value of that lock variable will be written. Value will be written. Okay, and if that value is false, that means nobody is using it, then we'll set its value to true. And setting the value of lock to true means somebody is using it. Okay, so lock will be obtained when the return value is false, that means nobody is using it. And if it is true, that means somebody already had the lock and using it. So that means you have to wait. Right? Exactly same thing happens when swap. It also does two things atomically. Okay, and what are these two things? Number one, compare the content of memory location to given value. We are exactly doing the same here. We are just comparing it with false. Okay, so compare the content of memory location. Now, what is this memory location? That memory location is my lock variable. Because variable itself is the memory location, right? We are already aware of that. So this lock will be the memory location. So compare the contents of memory location with given value. If they are same, modify the content of that memory location to given new value. It is something like, say, I want to compare it with test and set. Then it's interestingly what I can say is compare the value of memory location with false, and if it is false, make it true. If it is false, make it true. So making it true is like new value. We'll set the new value. Okay. So that is as simple as like that. A small demonstration I'd like to give here. Say for example, this is for test and set, and the same idea can be extended to compare and swap also. Fine. So have a look here. Test and set. Suppose this is one lock in the memory. Think this as lock variable whose current value is false. Currently its value is false, right? And this is one process called as, say, P1. Process P1 wishes to enter into the critical section, so it has to acquire this lock. Now how this can be acquired using atomic instruction test and set. Okay, so P1 will execute test and set instruction on this lock. And how it works is something like this. For example, the first part is test the lock. Previously it was false here. And meaning of false is the lock is available. Right? Just a minute. So in testing part, value of this will be written, which was false is written, and meaning of false is lock is available. Nobody else is using it. Okay. So see, lock is acquired here, and at the same time, value of true is set here. If any other process wants to acquire the lock again, other process would have lock because value of the lock is set to true. If the value of this lock is then and then only it is true. So that process has to wait. Right? So for example, again, if I move to next, set to true. So for example, currently value is true. Value of this lock variable is true, and lock is acquired by process P1. Lock is acquired by process P1, and suppose there are other processes P2, P3, and P4, and they are trying to acquire the lock. In very first instruction, what will happen? What will happen? They will get the value of true because it is true, no? First part returns the current value, which is true. And because it is true, process P2 will come to know that somebody else is using it. Same happens with P3 and P4. So this definitely ensures the mutual exclusion. Right? only P1. Now P1 is in critical section. Now suppose P1 now finished working with the critical section and P1 wishes to now release the lock. Right? P1 also release the lock. And releasing lock is nothing but just setting the value to false. So P1 has released and now it is false. Now as soon as this becomes false, now there is a rest condition between P2, P3 and P4. Now they will compete who will acquire lock. Now because P1 is scheduled right now, it set it to false, no problem. Now out of P2, P3, P4, whichever process is scheduled, selected by the scheduler, that process will get the value of false. Say for example, in this case, P2 got the value of false. So P2 will acquire the lock and P2 will update this value to 2. Say P2 updated value of this. So lock is with P2 and then the lock is true. The same thing happens with P3 and P4. They will come to know that the value of this lock is true. That means somebody else is using it. That is the overall idea of test and set. That is overall idea of test and set. Okay. So in pseudocode, this can be written something like this: Boolean test and set, Boolean star target. So because as I mentioned, it returns the value. So test and set returns the current value. So that is what the Boolean, because we are dealing with just true and false. Right? Okay. So test and set, this kind of instruction. Now you think this like as a function, but this will be executed automatically because actually it is single instruction. Okay. It returns the original value of pass parameter, set the new value of pass parameter to true. So what is Boolean star target? Think of this target as a lock. Return value is equal to target. Return value is equal to target. Set the value of target equal to true. You may wonder here, if I am not acquired lock, why to set it true? Think like if it is already true, that means somebody else is using it. If it is already true and if you overwrite it with true, doesn't matter, no problem. Okay. Only is if this return value is false, then and then only you receive the lock. If, for example, your target is true, your override value, no problem. What it returns is true. If true is returned, that means already somebody else is using it. It is as simple as like that. Okay. And now by using it, this is how we implement test and set. Now by using it, it is something like this: while test and set ampersand lock. So if they have written suppose true, this while condition becomes true and nothing is there. That means you have to just wait. But if it returns false, so previously nobody was using it, right? So with test and set, what I received is false. Then this condition becomes false. So it won't go into the while loop. It will directly go into the section. So if test and set receives the false value as an return type, that means you have got the lock. That is as simple as like that. And once you finished using this critical section, set the value of lock to false. That's it. Now between previous Peterson solution and this solution, idea is exactly same. Only thing is Peterson solution makes use of non-variables, and here we are making use of test and set, which is a single instruction provided by the processor. So definitely it is atomic. You got the idea? Are any doubt? If you have any doubt, please ask. Because similar kind of idea is extended for compare. It is exactly the same thing. Yes, any doubt in this? Because graphically also I am programmatic. So this is how test and set instruction. Imagine like this as the definition of test and set, and how to use it for locking is something like this. Here, if you check for false value, because retrieving or getting false value from test and set, that means this is false. Because while loop working with condition, so return value of test and set is used as a condition, true or false. Okay, fine. So now have a look at compare and swap. Compare and swap. Because compare and swap, single instruction be executed atomically. Within instruction, there is no what I can say interrupt. Between instructions, yes, there is interrupt. It returns the original value of past parameter value. Okay, so here you imagine this value is your lock variable. This is L, lock variable. Okay, so we'll read the value of lock variable into the temporary, and that thing is returned back, right? That means return the original value of past parameter value. Now set the variable value. So this value is what I can say lock. Set the value of lock to new value. So we are passing this one. When if the current value of lock variable is expected. So in simple terms, if I want to implement exactly same like test and wet, this is my lock variable. What I expect is false. What I expect is false, and the new value I want to set is true. Meaning of this is if the value of lock is false, set it to true. That's it. Okay. So if value, now why star value? Because this is a point variable. So if star value equals expected value, star value equal to new value, and return the temp, that is what original value. And if that you want to exactly use like test and set, same thing here. Now only thing is now integer values are used here. So see, for example, shared integer lock initialized to 0. So you imagine like 0, right? So lock is initialized to 0, meaning nobody is using it. Okay. Now while compare and swap, now this lock variable, if the value of this lock variable is 0, so this is what I expect. What I expect is 0. That means nobody is using it. If the value of lock is 0, set it to 1. This is the new value we want to modify. And what it returns is original value. So if I expected 0, and if it is not that, if it is not equal to 0, that means somebody else is using it, right? If somebody else is using it, do nothing. You have to just wait. And if the original value was as expected, like 0, right? Then definitely you will get access to the critical section. Once you're done using critical section, set the level to 0. So exactly same thing we are doing, just you need to replace 0 with false, 1 with true. Then it is same like your test and set. Okay, so this is the definition for compare and swap instruction. And now how to utilize it for lock? Yes, something like this. So this is compare and swap. Okay. Now this is one more example regarding fusion with test and set. So wherein you will find like weighting of I is equal to true, and then lock there, and that lock is now utilized with test. Once you got that key, you will go into the critical section. It is just one example, not that much important. Okay. Now problem with the compare and swap and test and set is uh, these solutions are because it is easy to understand, no doubt. But if you make mistake there, that will create a problem. So rather than provide access to low level instructions, it is better to have some sort of API kind of thing, application programmers interface. Okay, because these are all privileged instructions. So operating system designer have to provide some sort of like software tools for that. And one of such software tool is called as Mutex Lock. Mutex. This is the word use. Mutex. Mutex. You can imagine like mutual exclusion. Mutual exclusion. That is what Mutex is. So each and every resource will be safeguarded by these Mutex locks, right? And whoever want to enter into the critical section should first of all acquire the lock. Okay, use it. Once you're done using it, release the lock. See, previously also we done the same thing logical level, but the thing is we are making use of some sophisticated hardware instructions which will be available to the end user sometime. Better option is this software tool has to be in operating system design. Okay, so the lock will be some sort of a boolean value which will indicate whether that resource safeguarded by that lock. That is just true and false value, as we already seen for test and set and compare and swap. Okay. In addition to that, whatever this acquire and release operations are there, they must be atomic. So that is our basic requirement, and that is the reason even we started with enable interrupts and disable interrupts. Okay. Okay. As I said, they must be atomic. Maybe they have different of hardware atomic instructions, but only difference is rather than providing access to the hardware instructions directly to the application programmer, these acquire and Mutex locks will be implemented by OS designers, and they will be available as a software tool to the application programmer. So kind of abstraction is given here. And these Mutex locks are called as busy waiting lock, because if the lock or if the resource is busy, you have to wait. Okay, and that is the reason they are also called as spin lock. Mutex locks are also called as busy waiting locks, or also called as spin locks. As the name suggests, busy waiting. If the resource is busy, you have to wait. That is it's very simple meaning. Okay. So for example, how acquire is implemented is something like this: acquire while not available. So for example, available is lock here. While not available, that means if the lock is not available. Now looking at this code, can you imagine whether true value is busy or false value is? Yes, you can put your comment on chat. True means available or false means available. Anybody? Looking at this code, acquire. Exactly, false. So that means, say, now if I read something like while not false, okay, not false. So negation of false is true. So if it is not false, you have to wait. Once you're done, you make it available equal to false. Something like this. Okay, that is how to acquire the lock, and releasing lock available equal to true. Available equal to true. Is it exactly reverse, false or true? Because releasing, whenever I want to release the lock, I am setting its value to true. That means whatever answer you have given, like previously with compare and swap test and set, fine, that was false. But here it is true. Really available is equal to true. Setting it to, we are making it available for us. So if it is false, that means it is being used by somebody else. Okay. What do you mean? No, don't whether it should be true or false. Okay. So meaning of this is, it is false, lock is not available to you. The same thing in and set, they are utilizing false value. Here they are utilizing true value. That is only difference. Okay. So here the same thing. Do acquire the lock, go into the critical section, release the lock. Very simple. Here it is same thing. There is absolutely no change. Acquire lock. Where acquiring lock is what? Check whether it is available or not. If it is not available, wait. When it becomes available, make it false. When it becomes available, make it false, so that it won't become available for others. Okay, that is what acquire and release is. Now on the same lines, the Semaphore is implemented on the same lines of Mutex locks. Okay. This was initially designed by mathematician Dijkstra. Okay, so originally he given names as P and V, two operations. So semaphores, the more sophisticated way of implementing mutex locks, because mutex locks only work with true and false. Semaphores are now more generalized than that. Okay. So what is Semaphore? Semaphore is the software tool, I can say, implemented by operating system to provide inter-process synchronization. That is utilized for synchronization. So if you want to ask the definition of semaphore, yes, semaphore S is any integer variable. Remember previously we worked with Boolean variable, just true or false. Here it is integer variable on which two atomic operations are possible. Atomic is like uninterruptible or indivisible, right? And these two operations are wet and signal. These two operations are wet and signal. The mathematician Dijkstra originally called wet and signal as P and V. Now, why? Even though logically it doesn't matter whether you call it P and V, acquire and release, wet and signal, lock, unlock, you call anything. But like whenever you are giving gate-like exam, you will come across P and V, the operations P and V. Okay, so it is wet and signal, where meaning of wet is wet on semaphore variable S is written as, while S is less than equal to 0, it is busy waiting, otherwise value of S will be decrypted. Usually you don't have negative value used for synchronization, but some operating system utilize negative value to keep track on how many processes are waiting on that semaphore variable. Okay, now to make it simple, imagine something like if the semaphore variable's value is equal to 0, if value of S is equal to 0, that means it is not available. Like resources are safeguarded by Mutex locks, on the same line resources can be safeguarded using semaphores. So semaphore S is equal to 0. If the initial value of this is 0, what will happen? If somebody want to acquire the resource, he'll go through very first part, that is wait on S. And what wait does is, this is most important thing, it decrements the value of semaphore variable by 1. See, yes, minus is written there. But there's a condition to do this. What is that condition? If the value is less than equal to 0, you have to wait. That means when you can decrement, if value itself is greater than 0, then and then only you can decrement. Right? Now, if I remove this 0 and if think something like, let me delete this and assume that the value of semaphore variable is 1. If the value of semaphore variable is 1, wait on S, what will happen? While S is less than equal to 0, this condition becomes false, so it is not busy waiting. It will decrement the value. So this value is decremented by 1, which becomes 0 now. Right? Now, if somebody else wishes to enter into the critical section, we'll have to go through again wait on S. This time, value of this semaphore variable is 0, so it has to wait. Whereas what happens in case of signal is, suppose original process done using the critical section, whatever the resource updation, it will signal the semaphore variable. What happens in signal is, the value of Semaphore variable is simply incremented. So again, this becomes 1. And if any other is waiting there, that will sense the value which is greater than 0. It will come out of this busy wait, and again it will decrement it. So it becomes 0. That means it has a word lock. So we are just playing with integer value 0 and 1, where meaning of 1 is resource is free, meaning of 0 is resource is busy. That's it. And if it is 0, that means wait, simply wait. Okay, so this is the concept of semaphore. Mostly in all modern operating systems, semaphores are available. Like in Linux, Unix, in even Windows. See, POSIX semaphores are there. Anyways, we will see its implementation of POSIX semaphores also. All right. Two types of semaphores are there. One is called as counting semaphore, whose value is not restricted to 0 and 1. It is the integer value that can range over an unrestricted domain. Now, how to utilize it? How to utilize it is very, very simple. For example, suppose I have 5 printers. I got 5 printers. Then I can initialize my semaphore variable to 5. If one process comes and wishes to take a printout, it will go through wait on S, semaphore variable S, okay, whose value was 5, for example. So as we already seen, wait simply decrements value by 1, it becomes 4. So access to printer is granted. Another process comes, yes, it will also decrement, it becomes 3. Access to next printer is given. See, previous printer is already in use, because I mentioned 5 printers are there. Because 5 printers are there, I initialize semaphore to 5. So I don't want to restrict to 0 and 1 only. So such a semaphore is called the counting semaphores, where it can be utilized to mention about number of resources available. So it is not just whether that resource is available or not. How many copies of that resource is available? Okay, so for example, in producer-consumer problem, whatever the buffer length is there, you imagine like those many items can be stored at a time. So 5, 4, 3, then it becomes 2, then it becomes 1. So 5 processes have granted the access. Then it becomes 0. And if 6 process comes, it will check the value. It's 0. So wait on S will be blocked. So until and unless any one of previous first 5 processes finishes its, that is the use of counting semaphore. Whereas second type of semaphore is binary semaphore. What happens in binary semaphore? It is restricted between 0 and 1, false and true. And that is exactly same like your Mutex locks. The meaning of 1 is resources available, meaning of 0 is resources not available. And these semaphores can be utilized to solve the synchronization. The very, very simple synchronization problem is given here. For example, in this diagram, there is one process P1 and another process is there P2. Okay, process P1 executes some statement S1 and P2 executes some statement S2. And now, suppose my requirement is to synchronize the execution of S1 and S2. That means execution of S1 should happen before execution of S2. That is what the thing I want to synchronize. Okay, now this can be done by having one semaphore variable called as sync, something like this. Now you imagine whether P1 is scheduled by scheduler first or P2, doesn't matter. Okay, so I'll have a synchronization variable S whose value will be initialized to 0. Okay, now if P1 is selected first or P2 is selected, doesn't matter. Suppose P2 is selected first, now it will go through wait on sync. Wait on this semaphore variable sync. Now as I mentioned, it is initialized to 0. Sync is initialized to 0. It has to wait. because we know wait will decrement the value if the value is greater than 0. But value itself is 0, so it has to wait, right? That is a busy waiting. Now because P2 is waiting, maybe scheduler selected P1. Now P1 executes S1 first. Now S2 is not executed, it is waiting here only. And now it does signal sync. Because it does signal sync, what happens is value of semaphore sync becomes 1 now, not 0. And as soon as it becomes 1, this wait will be broken. It is come out of wait loop and it executes S2. That is how we synchronize. So S1 will be executed before S2. Okay. So that is how I make use of semaphores. Now semaphore implementation, better option what I'll do is in next lecture I'll show you one small program in C language. Anyways, this is available in Java also, Python also, but I'll go with C or C++, and I'll talk about the POSIX implementation. Okay, so today we'll stop here.